Second day of SCAPE 22. We'll start the morning with a reliability session. But first, we'll have a short announcement from Claire for the panel discussions.
Thank you. So good morning, everyone. So we are starting this second day. And as you know, we'll have a panel this afternoon. So really at the beginning of the afternoon. So we'll have 8 panelists. So people coming from the substrate, the devices, the end system integrators. And I just wanted to ask the panelists if they want to present some slides to kick off the panel session, just to go to the back office here and handle the slides that you would like to have. It's not mandatory, but it's just a reminder. Normally you have received an email from MeTech asking if you want to have these support slides. So that just to remember you that if you want to use them, then please go to the back office before 2 p.m. this afternoon. Thank you. We'll discuss this afternoon. Thank you.
Thank you, Claire. So now it's time for the first presentation, which is a recorded presentation. It's from Ivas Lelis, US, and it's titled SiC MOSFET Reliability.
Hello, everyone. My name is Ivar Sleus. I'm from the U.S. Army Research Laboratory. I'm sorry that I cannot be here in person in Stockholm today. I want to thank MeTech for its kind invitation, and I also like to thank my co-authors, my ARL colleagues, Daniel Haberset, Damien Urcioli, Eric Schorn, and Ron Green. The title of my talk is Silicon Carbide MOSFET Reliability, and today I'm going to focus specifically on the threshold voltage instability work that we've been performing at our lab the last 2 years. There are 2 specific aspects of that. One is looking at the effect of dynamic threshold voltage instability on dynamic on-state resistance. And the other aspect is AC stress degradation, specifically that occurs in trench geometry devices. So here's an outline of my talk. First, I'll give an overview of threshold voltage instability, contrasting threshold voltage drift with threshold voltage shift, and what I mean by those terms. Discuss the VT hysteresis, briefly discuss oxide trap mechanisms that are driving the VT drift, and then finally talk about what is and what is not a reliability issue. Then I'll go on and talk about VT hysteresis and as processed commercially available silicon carbide MOSFETs, comparing fast IV measurements with slow IV, and discussing the particular sensitivity of trench MOSFETs to a negative bias overstress. Then the next section will be on the AC stress induced degradation, also known as gate switching stress. I'll discuss the principal mechanism, which is a static VT shift due to seemingly permanent charge trapping and accompanying increase in VT hysteresis. And again, highlighting the particular sensitivity of trench MOSFET devices, and particularly from one vendor. And then also that this degradation can actually be annealed out. And then the last section, I'll talk about the effect of dynamic VT instability on dynamic on resistance. And their principal mechanism is simply the VT drift that occurs during device operation. And I'll show effects in both as processed devices and devices that have been degraded due to AC stress effects. So first, I'll discuss an overview of threshold voltage instability. There are 2 types of change in threshold voltage that we consider. One is we call VT drift, and the other is VT shift. VT drift is due to ephemeral charge trapping events that occur whenever a gate bias is applied. So here we see a shift in the IDVGS characteristics during a positive bias stress, resulting in a positive VT drift. VT drift is a manifestation of the natural dynamic variability in threshold voltage. It's observed in all as processed silicon carbide MOSFETs, even at room temperature. And it by itself does not represent a device degradation, because the The effect can be reversed by the application of an opposite polarity gate bias, which is the hysteresis effect, which I'll talk about in a second. Here on the bottom right, I'm showing the schematic of the ephemeral charging and discharging of near interfacial oxide traps via a tunneling mechanism. That's the driver for the VT drift effect. So VT hysteresis is the back and forth drift in VT that occurs when switching from one polarity of the gate bias to the other. VT hysteresis can occur from very early times. The first tunneling transitions are believed to occur around 0.1 picoseconds, and it's been measured out to very long times in megasecond time range, even tens of megaseconds in some cases. There's a continuum to this response. The VT hysteresis envelope is obtained by switching, systematically switching back and forth the gate bias for a range of different hysteresis times. So you get a positive VT drift under positive gate bias. So we call that high side VT pos. And we get a negative VT drift under negative gate bias, and we call that VT neg. And again, this is a measure of the inherent dynamic threshold voltage effect in silicon carbide MOSFET devices. Oftentimes, rather than plotting the hysteresis envelope, we'll just plot the VT hysteresis magnitude, and that's simply the difference between VT pos and VT neg. And it's a function of not only the hysteresis interval time, but also the measurement speed and the bias magnitude applied on both sides of, both under positive and negative bias. And here's, I'm showing a schematic of that, of how we measure VT hysteresis. In the bottom right, I'm showing the effect of measurement speed. So for a fast IV, we see this very large hysteresis envelope, whereas for a slow IV, it's much smaller, with the low side being very close to the low side of the fast IV envelope. So here's a brief couple of schematics discussing near interfacial oxide trap charging mechanisms. So stress time determines which oxide traps may change charge state during the stress. And the measurement time, or speed of the measurement, determines what is ultimately observed. And here in the center, I'm showing variation in the VT instability as a function of measurement time. The faster we measure, the larger VT instability that we observe, and the slower, the smaller the effect is observed. VT shift, on the other hand, is a change in threshold voltage due to a seemingly permanent charge trapping effect. It is determined by observing a change in static VT, and is not a function of measurement speed. Static VT is any stable reference point. It could be VT pos, the high side of VT hysteresis measurement, or it could be you could also use the low side of the VT hysteresis envelope. Now, VT shift is a potential reliability issue. Obviously, if it shifts too much positively, then you can have degradation in the on-state resistance, and if it shifts too far negatively, it can cause increases in leakage current. It may also cause an increase in the observed VT hysteresis if the VT shift is large enough due to a change in the gate bias magnitude applied. Also, should be noted that we can see an increase in VT hysteresis due to trap activation, as has been observed in some older devices due to bias temperature stressing. In the bottom right, I'm showing again that we see an identical VT shift using both fast and IV measurement techniques when to show a VT shift, because the VT shift is due to a fixed type of charge, and therefore it's measurement speed independent, whereas the hysteresis is very strongly dependent upon measurement speed. Now, talk about VT shift. If it's large, is obviously a potential reliability issue, but VT hysteresis, if it's small, it should not be a reliability issue, but if it is But if it too also gets very large, then there's a potential effect due to affecting dynamic on-state resistance, as I will discuss in a little bit later in the talk. So now I want to go on and talk about VT hysteresis in as-processed commercial silicon carbide MOSFET devices. So we looked at a whole series of 1.2 kV rated devices that we purchased between 2019 and 2020, a range of both planar and trench devices. So here I'm showing again contrast between a fast IV measurement and a slow IV measurement. Of course, a fast IV shows a much larger effect. We also are able to see more of the effect at early times by using a fast measurement. And I want to mention that in this case, I'm plotting the magnitude of the hysteresis. So this is VT pos minus VT neg for the various interval times. We observe a wide variation in VT hysteresis between the different vendors. And we always observe that, as you would expect, that the hysteresis magnitude increases with increasing interval time. And it's interesting to note that the two trench devices from two different vendors, that they had a sharper increase in the observed VT hysteresis with increasing interval time. Yeah, I want to point out that there's one planar DMOSFET offering that is a strong outlier compared to all the rest of the devices from the different vendors. It has much larger VT instability. It has instability about 3.5 volts at 10 microseconds and over 6 volts at around 10,000 seconds. On the right-hand side, I'm showing the slow IV, but now this is on an expanded voltage scale, so you can see some of the detail. And it's interesting to note, as you expect, the slow IV shows a much smaller instability, VT hysteresis, but the behavior relative to each other is basically the same. So the vendor M device is still the outlier of the largest VT hysteresis, and the two trench devices from the two different vendors also again show a sharper increase with interval time. Now, next thing we want to do is discuss investigation of negative bias overstress in trench devices. And the results I'm showing in this section are true for both devices from both trench vendors. So when this data set on the left, the conditions of the hysteresis were -4 on the low side and +22 on the high side to ensure that all devices were within spec when we were comparing one with another. But on the right, we investigate what happens if we apply larger negative bias. So I'm showing a result for vendor T, which is this blue curve, which looks as good as any device at very short interval times. And this is replotted here on the right. But then we also did a series of increasing negative biases, and we noticed that, so I'm plotting here from -6 to -14, there's a large increase in the magnitude of the VT hysteresis. And the effect doesn't saturate until we get about -15 volts. And at 10 microseconds at saturation, the VT hysteresis for the trench device is as great as 4.5 volts at 10 microseconds, which is larger than the VT hysteresis for the outlier planar device showed previously. Now, here I'm going to compare negative bias overstressing with positive bias overstressing. On the left-hand side is negative bias overstressing, and instead of showing the magnitude of the hysteresis, I'm showing the low side of the VT hysteresis envelope, VT neg. So now the order of the curves is switched. So -4 is up here, and -6 is highlighted, and -14. So as you go more negative bias, VT neg gets lower and lower. So shows that the main cause for the dramatic increase in the VT hysteresis is due to a strong negative shift of VT neg, the low side of the VT hysteresis envelope. It moves by over 4 volts. In contrast, on the positive bias overstressing, now we're looking at the high side of the VT hysteresis envelope, VT pos, for a whole range of positive biases applied. And we only observe, and so here it's important to note that the voltage scale is different. It's a 7-volt scale for the negative bias overstress to show the full range of variation versus only a 2-volt range here. And for any given hysteresis interval time, it's only a couple, it's less than half a volt variation. And we observe saturation by the time we get to about 16, 18 volts. So I want to mention that the VT pos, the high side of the VT hysteresis envelope, is a much better reference point for gauging changes in static VT for these trench devices. So then this next slide I'm showing a comparison of the trench device I just showed. I'm again showing the magnitude of the VT hysteresis envelope and comparing that to a planar device, again for the same range of negative bias overstress. And for the planar device, we observe that the full response saturates by the time you get to about -6 volts, and that VT hysteresis is well below 1 volt at 10 microseconds compared to the 4.5 volts we see for the trench device. And that difference may be due to that the gate oxide is on the silicon face of a planar device rather than the A face or M face of a trench device. And so there may be more charge trapping in those A face oxides. Next, I'm going to discuss AC stress-induced degradation. So following up on reports in literature that came out in 2020 about this AC stress degradation effect, we looked at it ourselves and we confirmed that we also see a large static VT shift that occurs. We also observed that there was an effective increase in the VT hysteresis that accompanied that. And we also found, as we'll show in a moment, that both degradation effects can be annealed away. And here I'm just showing a schematic. So we apply the AC stress, and then we do the hysteresis measurement, and then we return to the AC stress to produce this these curves. And once again, I'll point out the sensitivity of the trench geometry devices during a negative bias overstress to this AC stress degradation effect. So here I'm showing static VT shift for various devices, several different planar devices, as well as the 2 different trench vendor devices. And again, like I said, we confirmed that the trench devices are the most vulnerable, but only when applying negative bias overstress. But even more particularly, this effect of the trench device overstress AC degradation effect was primarily only observed in one of the 2 vendors, what we were calling vendor T. These are all randomly assigned letters, have no meaning, just drawn out of a hat. So the vendor T device shifts almost 10 volts at around 10 to the 13 total cycles, whereas the other trench, the vendor V, what we called, is saturates soon after you get to around 1 volt shift. And a couple of planar devices also shifted close to 1 volt, but then also tended to saturate. And also note that this is plotted on a log scale just so that we can see the early signs of degradation in the various devices. So now here I'm going to show VT hysteresis and how that changes with the VT shift due to the AC stress degradation. So again, the trench MOSFETs are the most vulnerable, but only when applying a negative gate bias overstress, and in particular only in what we're calling the vendor T trench devices. But we see greater than a 3.5 volt increase in VT hysteresis, because the original pre-stress VT hysteresis was down around 1/4 of a volt or so. And we believe that this increase in VT hysteresis is due to simply change in bias magnitude being applied during the VT hysteresis measurement because of the large VT, the large positive VT shift. And it's really important to note that no saturation is observed. So now I'm gonna focus on the effect of negative gate bias overstress and variation on the low side during the AC stress. And what we see here, looking at the VT shift, is that there's a small effect at -6 volts, and it's larger at -8, and we see the largest effect at -10. So the larger the negative bias, the larger this effect, and the sooner the degradation occurs. Similarly, when we look at VT hysteresis, we see a small effect at -8 and a much larger effect at -10. Again, the increase in VT hysteresis is driven by the VT shift. Looking on the other side, on the positive gate bias overstress, we looked at a range of voltages from +10 to +28. The two lower ones, +10 and +16, don't show much effect, whereas the larger one, the positive biases do, but there's, again, the effects tend to saturate. +28 is no worse than +22, and that's the same is true when looking at the VT hysteresis. So next we're looking at the AC stress-induced static VT shift as a function of frequency. Now these are not focused completely on the vendor T trench devices, because those are the ones that showed the large effect. And this stressing was -10 on the low side and +22 on the high side. So what we observe is that with the higher frequencies, the effect is observed sooner in time. But if we normalize all to the number of cycles, the various curves fall on top of each other. So it's clearly a function of the number of cycles, not frequency or time. We also compared dwell time versus transition time. And for dwell time, we see some small variations in VT shift curves, but no trend is observed. Whereas for the transition time variations, we see a clear dependence on transition time, and faster transitions lead to a larger degradation effect. And this must be due to electrons getting trapped in some deeper trap state where they are not able to tunnel back out with a change in bias. And this happens, the faster the transition occurs, the more likely this is to happen. And so this is happening under some very strong non-equilibrium conditions. We don't fully understand the mechanism, and that's something we're continuing to investigate. So here I'm showing annealing of the VT shift with the application of high temperature. So we looked at a variation of temperatures from 200 to 300 C, applying -10 volts, and we see that once you get to 250 C, you're starting to see most of the VT shift that occurred has been annealed back out, and 300 C is all annealed out by 10 to the 5 seconds. But it also requires that high temperature alone is not enough. It also requires a negative bias. So here showing the variation in annealing with applied bias. So positive bias +22 results in almost no annealing. 0 volts, about half of the shift is returned. And under negative bias, we see a full recovery. These were performed at 300 degrees C. So it requires high temperature and a negative bias, which are the negative bias that was similar to that was required to create the VT shift in the first place, which is interesting. So finally, in this figure, I'm comparing pre-stress with post-stress, with post-anneal. And in this case, we used a slow IV. All the other measurements I showed were using a fast IV, but this one we use a slow IV. So the instability, the VT hysteresis, we're showing the hysteresis envelope here. It's not as large as it would have been for a fast IV measurement, of course, but nonetheless, with the slow IV, you see the large positive VT shift that occurred due to the AC stress degradation. And then we also see that high temperature anneal under negative bias entirely removes this degradation damage. And so that the pre-stress and post-anneal hysteresis envelopes basically lie on top of each other. Now I'm going to discuss the effect of dynamic VT instability on dynamic on resistance. So this is the circuit setup that we use to perform the measurements. The key points are that the initial RDS on was calculated 200 nanoseconds after VGS reached crossed 0 volts during a turn on transition. So we calculate that by waiting 200 nanoseconds, the device was fully turned on, and we calculated RDS on. And then we calculated RDS on a second time immediately before the start of the MOSFET turn off transition, and then we calculated the percent change. So first result I'm going to show is for the planar outlier device, what we call vendor M. And this is the one with the large VT hysteresis as processed. And I'm showing here is a change, percent change in RDS on versus frequency. We looked at several different frequencies for 3 different temperatures, from 25C, 75C, and 125C. And so we see 2 things. One, larger change at lower frequency, which makes sense since there's more time for VT drift to occur for lower frequency switching. And we also see that this effect lessens with increasing temperature. But the main point is that large dynamic VT can result in significant dynamic RDS on. Here we're looking at a different example of another planar device. This had had one of the worst of the planar devices in terms of VT hysteresis, but much, much smaller hysteresis than the outlier device. And here, when we do the same type of comparison, basically see no dependence on frequency and a small effect regardless of which temperature, though higher temperature again did make the effect even smaller. So smaller dynamic VT results in a much smaller dynamic RDS on. And finally, here we're looking at the vendor T trench device. We're showing 3 curves, one for pre-stress, one after mid 10 to 11 cycles, and one after a little bit more than 10 to 12 cycles. And again, plotting versus frequency. Pre-stress, it's very flat and relatively small. As you start seeing degradation, the amount of dynamic RDS on increases, and it gets up to 70% at 10 kilohertz at room temperature. These are all room temperature in this case, for more than 10 to 12 cycles. We don't have the measurement for out to 10 to 13 cycles when we saw a 3.5 volt shift, but presumably that would be an even larger dynamic R-on effect in that case. So once again, large dynamic VT results in significant dynamic RDS on. So now I'll give the conclusions for each of the sections. For VT instability mechanisms, VT drift and VT hysteresis are observed to some degree in all silicon carbide MOSFETs, regardless of manufacturer. Measurement speed will always determine how much of this VT hysteresis is observed. Small VT hysteresis is not a reliability issue, but large VT hysteresis may be. And certainly large changes in static VT can also pose a reliability issue. VT instability in commercial silicon carbide MOSFETs, we observed one outlier among the planar DMOSFETs that have much larger VT instability than any of the other devices. However, trench devices from both vendors under negative bias overstress conditions showed just as large VT instabilities as the outlier planar device did. And that may be due to gate oxide being formed on the A face for trench devices rather than the silicon face as it is for the planar D MOSFETs. For the AC stress, results in the VT shift, which in turn causes an increase in VT hysteresis. Significant AC stress-induced degradation is only observed under negative bias overstress conditions, and then primarily in only one of the two trench devices from one of the two vendors. The degradation is dependent on the number of cycles, specifically cycles that have fast transitions, and with a low side gate bias that is below flat band into accumulation. That's when we see that degradation occurring. High temperature exposure together with negative gate bias is able to anneal out the effects completely if the temperature is large enough under negative gate bias of that AC stress. So you can anneal out the effects of the AC stress degradation. And then finally, dynamic on resistance. When VT hysteresis exceeds more than a few volts, significant dynamic RDS on is observed. The cause of this dynamic VT can either be due to variations in processing or due to some type of stress-induced degradation such as AC stressing. And large enough VT instability may result in significant dynamic RDS on effect, which in turn may be a reliability issue due to an unanticipated increase in power dissipation. So that concludes my talk. Thank you very much for your attention. And any questions, you can email me at this address. And thank you very much.
So, first presentation, thanks to Ivars Lelis. This morning's second presentation comes from Kei Bong Jung from K-Tech, and it's titled Reliability Issues in SiC Semiconductors for Automotive Applications.
Good morning, everyone. I'm glad to present at the SCAPE 2022 workshop. I'm working on Korea Automotive Technology Institute, KATEC. My name is Dr. Gyubong Yeon. KATEC is an institution that was invested by the Korean government and 1,000 auto part company with Hyundai Motor Company. Title of this presentation is Reliability Issue in Silicon Carbide Semiconductors for Automotive Applications, and introduce that automotive silicon carbide semiconductor based high efficiency and high voltage PTC heater system development. Contents consist of motivation, overview of PTC heater system for xEV, R&D goal, and content with reliability issue, commercialization and benefit, and summary. Motivation. xEVs are being developed with high efficiency and high voltage electric and electronic systems. It is required for the device transition from silicon IGBT to silicon carbide technology. This picture is show that semiconductor power device market for xEV. It is predicted that the proportion of silicon carbide will increase rapidly. Characteristic of silicon carbide power semiconductor is stable characteristic with wide energy band gap, and high current control characteristic with low loss and high frequency, and high reliability characteristic with low channel resistance and small device thickness compared to silicon power semiconductors. This picture is show that silicon carbide has high frequency and high power characteristic. Compared to silicon IGBT, silicon carbide can reduce a device chip size, as you can see comparison with the other different type of device. This slide shows the overview of project, PTC heater system, and a consortium organization. The PTC heater system is high efficiency and electric vehicle heater system using the positive temperature coefficient effect. This project will be supervised by Korean government. The general manager is SCAPE. The main development technology are performed by RISE for silicon carbide component, Levotech for the PTC heater controller, and URI for the PTC heater module. We expected that project product will be supplied automotive companies such as Hyundai Motor Company through Hano System. This slide shows development of PTC heater module and controller with silicon carbide. The replacement from IGBT to silicon carbide is required. It is expected that one silicon MOSFET is corresponding to 3 silicon IGBT. The PTC controller will be developed for functional safety technology as well as virtual qualification technology applied. Virtual qualification technology is a reliability simulation technology using the influence of temperature and vibration in harsh environment conditions. Fault in automotive systems are caused by thermal, vibration, and electromagnetic interference problem in harsh environment. Therefore, there are test method standards for individual problems. However, they are not independent. So standard test method using integrated fault injection is required. In recent years, the need for high functional safety semiconductor in vehicles, such as system on chip, with a high ASIL, automotive safety integrity level, in the area of autonomous driving controllers, has increased. The characteristic reliability test of semiconductor is important because it is safety in units related to autonomous vehicle, and it is at risk for the fault. This picture is show that for autonomous safety integrity level with ASIL D, C, P, A. In ASIL D, probability of violation of safety goal is required to be 1 fault in 100 billion hours. In ASIL D, single point fault metric is required to be less than 99%. In ASIL D, latent fault metric is required to be less than 90%. This picture is shown that AC, Automotive Electronic Council qualification. In automotive powertrain application, AEC grade 1 and 0 is required to be operating temperature from -40 degrees to 150 degrees. In automotive safety application, AEC grade 1 is required to be operating temperature from -40 degrees to 125 degrees. An important feature of HQ assessment test is that it must specify the electrostatic discharge, ESD, requirement issue. 3 out of 5 items are ESD items, and there is an important reliability issue. In harsh environment for xEV, the automotive fault is caused by being together with the thermal influence, vibration influence, and electromagnetic interference. The reliability requirement is increased. In order to secure reliability for automotive, we can plan to conduct development, reliability tests, actual vehicle tests. Woody industry that is involved in the project already supplied IGBT-based PTC heater system to Tesla in their business. When the project development complete, in the end, with RISE, we expect to be able to increase the global market share. We also look forward to expanding into various application fields through global joint research. Summary. xEVs are being developed with high efficiency and high voltage electronic systems. It's required for the device transition from silicon IGBT to silicon carbide technology. The automotive fault is caused by being together with thermal influence, vibration influence, and electromagnetic interference. The automotive reliability requirement is increased. In order to secure reliability for automotive, we plan to conduct development, reliability tests, and actual vehicle tests. Thank you for attention.
Thank you. Do we have time for some questions? Any questions?
That's right. 800 voltage, but safety margin includes safety margin because 50%. 이게 뭐라고 해야 되죠?
Okay, so
세이프티 마진 때문에 이게 50% 정도 해서 1200볼트까지 커버를 해줘야 된다. 예, 닥터님, conversation, please.
This application, they want to increase the 50 safety margin. That's why they want to increase increase the voltage capability instead of the 650 volt instead. Yeah.
thank you. So is the automotive in Korea primarily working on 800 volt battery or the 400 volt that's more common today?
Yes.
한국에서는 800 볼테이지가 커먼으로 사용하는 건지 아니면 400 볼테이지로 사용하는지 지금
800.
Yeah, it's 800 very commonly. Yeah.
Thank you very much.
Okay, we have a second question here. Please.
My question is regarding the AC level that you have mentioned.
Yeah.
Which AC level you have done the design? Which AC level you have designed the system?
We can 뭐라고 해야죠? We can make up AC level T. We need for 얘기 좀 해주세요. AC 레벨을 어디까지 확보를 할 거냐고 물어보시는 것 같아요.
네. 답이 뭔지.
답은 AC 레벨 T.
예?
AC 레벨 T.
Yeah. H level D. Is that correct?
In the chip level or in the system level?
Is a system level or okay, 시스템 레벨인 건지 이게 Hback 레벨인 건지 800 볼테이지가.
800볼트가
네.
지금 H100 레벨이냐고 물어보신 거예요?
예.
아, 예. 그렇죠. 예.
Yeah.
EV 쪽이니까.
It is correct. HVAC level. HVAC. Yeah.
예, 전체 H100 시스템이 전부 다 800볼트.
Yeah.
예.
It's overall HVAC required 800 voltage level.
Sorry about
Thank you.
broken English.
Okay, thanks. Let's thank the speaker. Looks like we are a few minutes before the schedule. So let's take advantage to start slightly in advance. So, next presentation is a recording one, which is Subhashish Bhattacharya from North Carolina. Use of 10 kV SiC MOSFETs in converters and their performance under critical conditions.
Good morning. I'm Subhashish Bhattacharya from NC State University, Freedom Center, and Power America. And unfortunately, I'm unable to attend in person. So I'm going to actually present this through my recorded Zoom. And I'm going to talk about the use of 10 kV silicon carbide MOSFETs in converters and their performance under critical conditions. So as a first step, I would like to actually present the use of the 10 kV MOSFET for solid state transformer. And this is a project which we did for the Navy, where we actually delivered 100 kVA 4160 volt to 480 volt solid state transformer with the 10 kV MOSFETs to the Navy in this container. And this is actually installed at a naval base. So the SST that we delivered is actually based on 10 kV MOSFETs. So we have a medium voltage grid and a front-end converter, active front-end with the 10 kV MOSFETs, a DC to DC converter, which is a dual active bridge, again with 2-level 3-phase, and then a low voltage side, which is deployed by 1200 volt devices. So here's the complete schematic. The AFIC is switching at 10 kilohertz. The DC to DC DAB is switching at 20 kilohertz. And here is the complete waveform of the prototype. And we are operating the DC bus at 7.2 kV for these 10 kV MOSFETs. And as you can see, the very clean waveforms for the AFIC as well as for the DAB. The peak efficiency that we measured is 96.8% at around 36, 38 kVA. And this is put in the container as you see here, and here is the power density of the SST. So what motivates the SST from the founding of the Freedom Center, I'm one of the founders, we actually said that the SST was a hub that could integrate renewables and connect with the grid. So that is one of the motivations for the SST at medium voltage. Then, of course, the DC microgrids or the DC grids is a big motivator for the SST, where we interface at medium voltage with the AC and then provide a medium voltage DC as well as a low voltage DC grid. So coming back to this project, the solid state transformer, as I said, that this is what we implemented, where again, we use the 10 kV MOSFETs in a very simple 2-level converter for the AFEC and for the dual active bridge 3-phase. And again, 1200 volt devices on the low voltage side. We developed the medium voltage gate driver for this MOSFET. We also developed the low voltage side gate driver. And this is controlled by an industrial controller, which is a NI compact Rio. Here are the specs of the system, and at 100 kilowatt, 7.2 kV DC bus. So again, a little bit about the 10 kV MOSFETs that we used. We used this XHV-6 as well as the XHV-9 modules. And for one switch, we have 6 dies in parallel. And so this is a half bridge. This is the measured IV characteristics of this entire module. And we drive these gates at 20 volt. And the measured RDS on of this device is around 65 milliohms and to 181 milliohms as a function of temperature in the operating range that we are operating. Switching performance at both 3500 volts as well as 7200 volts are given out here, where you can see the turn off energy as well as the turn on energy as a function of the temperature. And these are the things that we first do to characterize, particularly for our thermal management. We are limiting the dV by dTs to 40 kV per microsecond in this particular project. So here again is the setup in the lab that you can see on this left bottom. It is a modular system where each of these 3-phase blocks are these modules that you are seeing out here. And the 3-phase high frequency transformers are shown out here. Each of these transformers is 40 kVA. This is the package inside the container. This is the container, and this is the testing that we did in the container. Here are the final results of the entire SST at a reduced voltage or half voltage of 3.5 kV and 600 volt on the low voltage side DC at an active power of 28 kilowatt. And again, you can see the low voltage side switching the medium voltage side and the dual active bridge 3-phase converter waveforms at 28 kilowatt and at 3.5 kV DC bus. Then we go into the full operation of the system with a DC bus voltage of 7.2 kV, and this is interfacing a 4160 volt on the AC grid side and delivering around 400 volts at 30 kilowatt on the low voltage side. So here you see the AFEC or the front end switching at 10 kilohertz with a peak current of 25 amps and 30 amps at a steady 7.2 kV DC bus with a very simple topology, 2-level topology, and the clean currents. Again, the dual active bridge with a phase shift of 20 degrees transferring 17.5 kilowatt and 30 degrees transferring around 30 kilowatt. So again, we are showing the performance of these devices at 7.2 kV with the 10 kV MOSFETs. To do all this project, we had to develop each of these components. For example, the gate drive. So we actually developed an intelligent gate driver at NC State, which has a CPLD on the gate driver, an active gating, and a DSAT protection. And of course, the gate driver power supply, which is isolated for 15 kV. And you can see the coupling capacitance of this power supply transformer is around 1.43 picofarads. This is an active gate driver. So as I said, we can control the gate resistance dynamically. And here we are showing that we can control the VGS and we can control the Miller plateau as required dynamically by the CPLD and by changing the RG of the gate resistance. I mentioned that there is a DSAT protection. So we are actually showing the short circuit performance of this device. So with a 6 kV DC bus, we intentionally cause a short, the gate driver detects it, and then actually shuts it off in 2.4 microseconds. So this is done on a single die, and the single die is supposed to carry 15 amps, but the device current goes to around 220 amps, but the device does not fail, and the gate driver is able to turn it off. So let me actually talk a little bit about the short circuit protection of this 10 kV MOSFETs. So we, as I said, we use a high voltage DSAT diode, which is a 8 kV diode, silicon carbide JBS diode. Then of course, in the gate driver, we have a soft turn off and an active Miller clamp. Now, from our experiments, we have done all these for all the devices from 3.3 kV all the way to 10 kV and even up to 15 kV MOSFETs and 15 kV IGBTs. We can actually then figure out the short circuit SOA. So for example, for the 10 kV device at 6 kV, we have around 8.1 microseconds of short circuit SOA. So again, I'm showing you the same result here, where I'm trying to show you that this was done on a single die, a single device. And again, we are successfully turning off with the gate driver in 2.4 microseconds at a 6 kV DC bus. And the calculated junction temperature at that point is around 762. But this is a golden package or a metal can. So we are not actually constrained by the packaging for this particular device. So based on this, again, as I mentioned, that we actually do the short circuit SOA at different DC bus voltages. And again, with lower voltages, obviously the short circuit time, withstand time is going to be greater. And we get around up to 6 kV. We can safely do at least 6 microseconds to 7 microseconds of short circuit time. This is, we do a short circuit of this device with our intelligent gate driver as a function of the voltage from 1000 volts to 6000 volts of VDC. And the reason why we are doing this is because we are interested actually to figure out the short circuit IV of this device, and for different devices, we have done the same thing. So for 3.3 kV, 6.5 kV, and 10 kV dies, single dies, which are at different current ratings, now you can see the short circuit IV and the saturation current as a function of the VDS. These are the different devices with the different active areas and the drift layer thickness. So from here, we can also calculate the amps per centimeter square or the current density as a function of the VDS. The next very important point is the avalanche characteristics of these devices. So what happens during avalanche? So if you take the 10 kV device and you do an avalanche, the avalanche energy is around 7.65 joules. So these devices or these dies are very robust. They are very high avalanche energy, and the avalanche voltage is around 15.8 kV. So this is something very interesting because the device can actually go up to 15.8 kV, not fail. And this is the avalanche voltage. And of course, we have the avalanche time, and this experiment was done at 1200 volts. So depending on the avalanche current, we can actually then plot the avalanche time. Of course, the avalanche voltage, the energy remains pretty much the same. I want to then mention another particular project with the 10 kV MOSFETs, because I'm concentrating on the 10 kV MOSFET and its use is a solid state transformer. But this solid state transformer is actually going from medium voltage to medium voltage. So what is the use of this solid state transformer? The use is that if one wants to interconnect microgrid to microgrid or a microgrid to a grid, then we need this kind of a bidirectional solid state transformer to control the import and export of power, as well as provide galvanic isolation. So this is the value proposition of this particular project. And to implement this project with the 10 kV MOSFETs and to go up to a medium voltage of 13.8 kV on both sides, we have to use a 3-level pole. We are using a 3-level pole, but then each switch of the 3-level pole has 2 devices connected in series. So then we can now block around 24 kV of DC bus that is required for the 3-level for 13.8 kV, and with 2 of these 10 kV MOSFETs per switch. So each pole is a 3-level. Again, we have a AFEC, which is switching at 10 to 12 kilohertz. We have a DC to DC dual active bridge 3-phase converter, which is now switching at 20 kilohertz. And again, AFEC on this other side, or an inverter. So we have actually implemented this entire system in the lab. Here is experimental results of one pole where, again, we have two devices, two 10 kV MOSFETs connected in series. The dynamic voltage balancing is done by snubbers, as you see out here. And the static voltage balancing is done again by resistors. And this is a NPC topology where we have clamping diodes. So this is the half bridge in the lab. This is the thermal management. Everything is on a cold plate. And here is experimental results at low voltage with 2.5 kV, around 10 amps, 60 hertz fundamental, but switching at 12.5 kilohertz. To do this, to go to this point, we actually had to first do the sharing or the dynamic voltage balancing of the two series MOSFETs. And here I'm showing you a turn-off waveform where two series MOSFETs are connected with 12 kV DC bus. And again, you see this is the VDS of the MOSFETs turn off, with both of them sharing around 6 kV each with the 12 kV total DC bus and during the turn off conditions. So with this, as I said, we have the entire solid state transformer built. Here is the front end, three phase, and this is one pole of that three phase. So you're looking at only this part here, and we have three of these three poles to make up the AFEC or the front end. And we tested this thing at 25 kilowatt, 5.5 kV DC bus. And now you can see the waveforms here. So these are line-to-line voltages measured at the load points A and B. And then again, you can see the pole voltages, the pole currents, sinusoidal switching at 10 kilohertz. And as I said, with 5.5 kV DC bus. And very nice line-to-line voltages after the filter. So for this particular project, the DC to DC is again a three-phase dual active bridge with the three poles as I've shown. And here is the experimental results of the dual active bridge three-phase working with at low voltage again. This is only at 1 kV, but everything is switching at 20 kilohertz. So all the poles with two series connected devices per switch and a three-level NPC pole based DAB is switching at 20 kilohertz with the transformers. And now you can see the voltages and the currents of the two phases. Now I want to take you to another solid state transformer, which we did some time back, where we actually implemented that with the 15 kV IGBTs. And so now with the 15 kV IGBTs, you can go with a single device with a three-level pole and 13.8 kV DC bus. Again, the topology is similar, where we have a AFEC, which is now switching at 5 kilohertz for the IGBTs, and a dual active bridge where we have a 10 kilohertz switching frequency and a three-level pole on the medium voltage side, and two converters with two levels with 1200 volt MOSFETs on the low voltage side. And again, the inverter is 1200 volt MOSFET based. So this entire system was built and grid interfaced at 4160 in the lab and with 8 kV DC bus. And now you can see the AFEC with the grid currents and the converter pole voltages on the grid side switching at 5 kilohertz at 8 kV DC bus. This is again the grid side voltage, the grid side current. This is the high frequency transformer. This is a 70 kVA transformer at 10 kilohertz, and the rating of the transformer is 22 kV to 800 volts. And this is the low voltage side converter. So results of this, the dual active bridge switching at 8 kV DC bus. So on the medium voltage side, you see a three-level waveform with the current, and on the low voltage side, this is one of the LV side voltages, the delta voltage, as well as the current. This is the transformer. Again, for this high frequency transformer, you can see the size of this at 70 kVA, 10 kilohertz, how small this is, and this is oil filled, and these are the parasitics of the transformer. Now, a little bit of the comparison with the IGBT versus the 10 kV MOSFET that I've been talking about. So with the 15 kV IGBT, the motivation to go there would be higher current density with a smaller die. So you can now see that this die is 8.1 millimeter by 8.1 millimeter. This is a 20 amp die at 15 kV. There are two JBS diodes which are connected in series because they're blocking 8 to 10 kV for this co-pack. This is the IV characteristics. And we did actually something interesting, which is the short circuit of this device. So we varied the DC bus from all the way from 1 kV to 8 kV, and we are intentionally causing a short circuit, and we're turning it off after the saturation current. So we are confident with our gate driver to do this. And for the IGBT, because it's a bipolar device, now you can see that the gate voltage actually has a peak. This is not something that you would see with a MOSFET, but with the IGBT, you would see where the gate voltage peak can go all the way up to 40 volts. So here is one of the results here with up to 8 kV. And again, you can see the current goes all the way up to 258 amps. The die is only rated for 20 amps. So if we compare apples to apples, or if we compare the IGBT with the MOSFET here, the 10 kV MOSFET and the 15 kV IGBT, now you can see the turn-off waveforms for the gate voltage. And this is the difference that in the MOSFET, because of the unipolar device, the gate voltage does not peak up. And that is good for the MOSFET because of there's no degradation in the gate oxide. For the IGBT, we do see this. And again, as I said, for the short circuit, for the MOSFET, as I've shown here, we are turning off these dies at 6 kV in 2.4 microseconds. For the IGBT, again, we go all the way up to 8 kV. So with that, I want to actually end my presentation. And I really want to thank the organizers for giving me this opportunity to present. Unfortunately, I could not attend in person and present and have discussions with you, but please feel free to email me and look at our papers. And if there's any interest in actually collaborating with our group out here, and my colleague, Dr. Victor Viliadis, is attending in person, please reach out to him also. And I welcome the discussions and any feedback and questions. Thank you very much.
So, thanks to Mr. Bhattacharya. It's an awful echo. I think I do like this instead. Like that? Okay, slightly better. So let's welcome our fourth speaker, Felix Hoffmann from University of Bremen, with a presentation titled Power Cycling of SiC Power Devices, Aspects and Peculiarities. The floor is yours.
Thank you for the nice introduction, and good morning, everybody. So I want to talk today about aspects and peculiarities of silicon carbide power devices, particularly with respect to power cycling. Now let me first give you an overview about the issues I want to address today. So first of all, silicon carbide has a more than 3 times higher Young's modulus compared to silicon. This, of course, increases the stress on the chip interconnects and hence reduces the reliability under thermomechanical stress. Secondly, we have already heard about the issues related to the MOS system and also the effects of VTH hysteresis as well as VTH drift. In this picture here, you can see the shift in the right direction. However, as we heard earlier today, both positive and negative shifts are possible. And also, if we look at the bulk material, also epilayers of silicon carbide, we see still stacking folds, which cause the phenomenon of bipolar degradation as we also heard, I think, yesterday. And last but not least, if you look at the devices from different manufacturers of state-of-the-art silicon carbide MOSFETs, you see a significant difference. So we have difference in packaging, which means basically bond wire diameter in numbers. We also have difference in chip dimensions, and we all know we have also still trench and planar gate structures commercially available. And also due to this difference in device design, we also see a significantly different temperature dependence of the RDS on. You can see this here as illustration for a couple of manufacturers, and you can see even though that two devices might have a similar RDS on at room temperature, the RDS on at elevated temperatures can be significantly different. And the question now is, how does those effects impact our power cycling? And I want to address today in two different chapters. So first of all, I want to assess it towards the precision of the junction temperature estimation, since thermomechanical stress heavily relies on the temperature swing. This is a crucial measurement parameter to interpret test results. And furthermore, I want to address the device degradation failure criteria and their ramifications for silicon carbide MOSFETs. So I start with the junction temperature estimation. Oh, this was a bit fast. Here we go. So when I talk about junction temperature estimation, I talk about the estimation by the VSD method, which relies on the body diode voltage drop at low current densities as the temperature-sensitive electrical parameters. Now, some of you might follow different approaches, but this is a very well applicable and a very well-known approach. And it's also used in a similar fashion for silicon IGBTs. So, of course, why is it always continuing? Anyway, so of course, if we look at a MOSFET structure, we have the MOS channel in parallel to the PN junction, which means if we want to use the PN junction as a temperature sensor, we need to have the MOS channel entirely closed. Furthermore, of course, we cannot have any external Schottky diodes, as they would deteriorate our measurement. Now, if we look at the very basic circuit topology of a power cycling test bench utilizing this method, you see this here with the DUT here in orange. And during the heating phase, we force the current in forward direction through the MOSFET while we turn on the gate here. And then the device heats up here by its own power dissipation. And when it reaches our targeted maximum temperature, we're going to turn it off. And then we inject a small current here into the source of the device and then turning off the gate. And then we have here the voltage drop of the device. And if we have a closer look here, we see it's actually quite dynamic. And if we have the relationship between temperature and body diode voltage drop at our chosen sensing current density, we can directly get the time-resolved junction temperature during the cooling phase of our device. And this way we can extract here the maximum as well as the minimum temperature. Now, which of the previously mentioned effects can actually deteriorate this measurement? Let me start with bipolar degradation. It is a well-known phenomenon for silicon carbide. However, we can also see that this can occur at fairly low current densities already. You can see this here for a silicon carbide MOSFET chip at a current density of only 60 milliampere per square centimeter, and you can see it's already operating in bipolar operation, visible here by the electroluminescence. Now, if this occurs, then the stacking folds present in the bulk material or epi layer can expand and then increase the forward voltage drop of the device, even at the low current density. And since this is more affecting the device when it is cool, it affects the minimum temperature reading rather than the maximum temperature reading. You can see this here as an example for two similar devices. And if you look here at the minimum temperature in blue, you see for DUT1 it's pretty stable, as you would expect it during power cycling, while for device 2 here you see that it's actually slightly decreasing, which is an effect of the increased voltage drop due to bipolar degradation. Now, if you look at that, the effect is not too pronounced, and its good thing is it's very well observable. So if you obtain the temperature, the characteristics of the temperature versus source drain voltage drop before and after the test, you can see actually a shift of the curve. And since this is not too pronounced, if you don't have a heavy bipolar degradation for your device, then this effect is not too problematic for power cycling, at least when you consider this only to use the MOSFET as heating and not the diode for heating, but that's a different story. So secondly, we already heard about the impact of the MOS system. So as I said, we need to make sure the channel is entirely closed. So for this, we need a sufficiently negative gate source voltage. You can see this here as an example for two different current densities at different gate voltages. And for this particular device, you can see that at -4, we still have a significant impact of the channel current. And only at -6 volt here, you see that a further decrease in gate source voltage does not lead to any change or any significant change here in the voltage drop. Now, this, of course, is highly design dependent, so it can be significantly different for different device designs. And furthermore, for some designs, it must be necessary to choose a VGS off beyond what the manufacturer specifies as VGS off max. And a good way to determine this is to assess the gate voltage versus the source drain voltage and look where we have no further effect of the gate source voltage on our body diode voltage drop. So now, even still, we found our VGS off, which is sufficient to close the channel. Left shift of the VTH, as we previously have heard from Ivars Lellis, can then lead that we still have a significant channel current, and hence it can deteriorate our temperature reading. However, this effect can mostly be avoided for most of the device designs if proper measurement parameters are applied. So if the gate source voltage drop is chosen to accommodate for some sort of VTH drift and also a proper sensing current. So how can we estimate, or how can we get a idea of how precise our measurement is, or in other words, if we have any issues with it? So we have some characteristics which may indicate that we have a wrong temperature reading. So first of all, if you look at the temperature dependence of the drain source voltage on the gate source voltage, this is basically the slope of the previously shown curve, and the Y scale here is logarithmic. So, and if you look here at our chosen negative gate source bias, you can see that if you have a very low impact, you can assume that the gate source voltage works. Also, the sensing current density, of course, plays a role. And for this, you can rely on the physics behind this measurement method. So it should be, according to the physics, perfectly linear, or almost perfectly linear. So, and you can see here, if you have a very weird configuration, you can get a very nonlinear characteristics. So this can give you a hint that your reading might be off. And last but not least, if you perform a power cycling without load or with very low load, where you don't expect any significant temperature swing, you can assess whether your measurement also does not show a significant temperature swings. If you have some sort of effect of the VTH shift or VTH hysteresis or nonlinear calibration curve, this might very well give an indicator that you have a wrong temperature reading. However, this is only some hints, and it cannot guarantee you to have a precise measurement. And to be sure, you really need to verify this temperature estimation, for instance, by thermography. And this needs to be performed for each device design if you really need to want to make sure that your reading is accurate. Now let's talk about the second chapter, the impact of device degradation and failure criteria. So as we all know, or I previously mentioned it already, the Young's modulus of silicon carbide is much higher. So it ends, or it leads to a lower cycles to failure. So if we compare two device designs, a silicon IGBT and a silicon carbide MOSFET with similar electrical ratings, you see that the silicon IGBT here in blue has a significantly higher number of cycles to failure. And this is actually around 20 to 30% of the silicon carbide MOSFET can reach 20 to 30% of the number of cycles to failure of a comparable silicon device. And this is quite consistent also for different designs and different work groups, so at least for high temperature swings. However, if we look further down at lower temperature swings, we see that the silicon carbide MOSFET seem to gain on the silicon IGBT towards lower temperature swings in terms of number of cycles to failure. What that means is we cannot just simply take the lifetime models we have for silicon devices and apply them for silicon carbide. So we really need to have a suitable lifetime model and verify whether it is the case to do our lifetime modeling. As we heard on the tutorial on Sunday, we can have an impact of the VTH shift on the power side, on the drain source voltage of our device during power cycling. So you see this here's an illustration. It is taken basically from what Francesco Inucci was showing on Sunday. And you can see that you have here a right shift between the first cycle and 100 kilocycles, for instance, here. And this shift here leads to a significant increase in power dissipation here, and subsequently, of course, also to an increase here in temperature swing. So it significantly accelerates the degradation and also reduces the number of cycles to failure of this particular device. It gets even worse, however, because if you apply a fixed failure criterion, which is pretty common, for instance, 5% increase in drain source voltage, you can reach this failure criterion without package degradation even occurs. And this is a problem because the power cycling test usually is targeted to assess the device's integrity towards thermomechanical stress, and there are either bond wire liftoff or chip solder degradation as a failure mode. And this can trigger an undesired failure mode. So now how to avoid this? I mean, the first part, so the acceleration, cannot be helped, but we can at least make sure that we choose a failure criterion which does trigger only at our desired failure modes. And this we can make sure for bond wire liftoff by not applying a fixed failure mode, but rather consider the first step increase in drain source voltage as our failure criterion, which indicates bond wire failures. So let's now discuss the impact of the device design. As I said previously, we have significantly different device designs on the market, and particular discrete devices differ in number and diameter of bond wires. Also, the mold compound is different, and also we have differences in the chip design, which also include the chip thickness, as some manufacturers thin their chips, and also difference in gate technology. Now, if we look at data obtained from two different manufacturers for similar or comparable devices, we see that we actually have a significantly different lifetime curve here. And what we see also is that towards lower temperature swings, we see that the lifetime model underestimates the number of cycles to failure obtained during power cycling. Now, of course, you can argue now that this is due to the package, because, of course, different manufacturers would package the devices differently. What we did now was having two different chips packaged on the same line and with the same packaging technology. So we kept all the packaging parameters as similar as possible. Yet what we see here is that we see a significantly different lifetime curve, even for two dissimilar chips in an identical package type. So we have a strong suggestion here that we have a power cycling capability which does depend on the chip parameters and not only on the packaging. However, those parameters are usually not considered in lifetime models. So since those are not fully understood, there is, of course, further work necessary to investigate this. But in any case, if a lifetime model is applied for silicon carbide MOSFETs, it needs to be made sure that the model actually works. This cannot be done by just simply performing power cycling at a single temperature swing, but multiple temperature swings are necessary. So, all right, let me conclude my talk here. In this talk, I talked about several silicon carbide specific effects which can impact the test parameter and test conditions during power cycling. And the main challenges are to achieve accurate and stable online junction temperature reading. Furthermore, detecting and separating undesired silicon carbide specific effects from the desired package degradation, and also obtain consistent failure criteria while avoiding undesired failure modes. As for the future prospect, the difference in power cycling performance of different market available designs cannot be attributed only to the package, but also the chip plays a significant role. And since they are not known yet, we need to further understand and quantify their impact. That's it from my side. Thank you very much for your attention. I'm now happy to answer your questions.
Thank you, and time for a few questions.
Very interesting presentation. Thanks a lot. So I'm of course curious on the root causes that different silicon carbide MOSFETs in the same packaging line behave so different. Do you expect this more on the material side, like metallization schemes to play a role, or are these really some topics of the design, like for example, topology differences in height towards the edge termination and so on? So what do you suspect, and what tests are you doing in the future?
So one of the strong correlations we find is that the chip thickness plays a role in the slope of the lifetime curve. So if we look at this curve, for instance, we see a very consistency that the thinner the chip, the steeper is the slope. However, we have some different other factors here as well. So I don't think it's likely this is the only factor, and others are probably playing a role too, which we have not looked into yet. But yeah, we will further try to check on the thickness and quantify this impact. But it's not that easy to do, because for this, if you want to rule out the chip design impact, then you must have the same chip design with different chip thicknesses. And since we don't manufacture our devices ourselves, that's pretty hard to do.
Can you reiterate, do I understand it right, that thinner chip, that first of all, it's the backside which delaminates? Do I understand? No.
This is only a bond wire lift-off.
Bond wire lift-off, okay.
So if you talk about discrete devices, the most common failure mode is bond wire lift-off.
Bond wire, okay. And thinner chip, they degrade faster?
Yes.
No.
Thinner chip, so what you can see here, it's just coincidence that they have the same power cycling capability at delta D100. This is really coincidence. And if you look at different devices, you see a whole zoo of lifetime curves. So the absolute number of cycles the failure depend on significantly different other parameters. What I'm talking here is only the slope of the lifetime curve here. And this is, we see a consistency between the chip thickness and the slope. And thinner devices have a steeper slope compared to thicker devices.
And it is always the bond wire?
Yeah, we only consider bond wire failures.
One last question.
You have two types of packages, without base plate and with base plate. And then you have two types of models commonly used to extrapolate this number of points, like coffin model and SCAPE model. Which model is well suited for which type of power modules?
Well, I mean, first of all, those are all discrete. So technically, none of those models are meant to be used for discrete devices. They are all established for modules. However, in general, the models mainly consist of a Coffin-Manson term. Sometimes you have an Arrhenius term of the minimum temperature, and sometimes you have a whole lot of other parameters. But the main impact factor is a temperature swing considered by Coffin-Manson term. And this is a simple approach we chose here as well. Of course, we also tried to use more sophisticated models. However, they were not really improving the accuracy on those parameters. So if you want to have a rough estimation, the simplest approach is the Coffin-Manson. And all the others you need to have a lot more tests in place and vary a lot of parameters to obtain the other parameters of more sophisticated lifetime models.
The accuracy of model, Coffin versus the other model, which is more advanced model with a lot of sets of parameters.
Yes.
Which one is well suited for SICK devices?
Well, none.
Thank you.
I mean, you cannot say this in general because you see so much different characteristics of different devices. So there is no general answer really. For some devices, it might work just good. So we have seen that as well, that you can fit the results for some designs pretty good with a simple Coffin-Manson. I mean, you can see it here. Well, next slide. This one here. It works just fine. It's almost absurdly good, this fit. So it just depends really on the device design. You need to verify this for your particular design.
Okay, let's thank the speaker again. The last presentation of this session. So now it's time for coffee, and the next session starts 11 o'clock. See you then.
Please stay a little for a while. I have very short announcement before the workshop is over. We have at our disposal also a smaller room very close to the coffee area. So if you have a need for some private discussion or a meeting or conference home or something, just tell me, I give you the key.